So looks like people had a chance to at least think a little bit about this. Right, I mean, it's fairly basic. It feels fairly basic, I think. But I think it's good to like visualize what this looks like in multiple dimensions. I guess I'll ask a first question. How many of these are actually more than one dimension? Are these all 2 or 3 dimensional or any 1 dimensional? Yes, Ryan?
1 and 2 would be 1 dimensional.
Yeah, so what's the dimension that you have changes in 1 and 2?
Just the radius.
Just the radial dimension, right? So we've actually solved 1 and 2. We've solved those exactly before. Like we've done that. We have the solution, right? The sphere is the temperature changes as 1 over r squared, or 1 over r, sorry. For the cylinder, or the temperature changes as natural log of r. So we've solved those exactly with, like, we know the outside temperature, we know the inside temperature, we've done that. The only one that's truly 2-dimensional is this bottom one here. That actually is 2-dimensional, right? You have changes in x and in the y direction. But what's happening in that bottom one is still governed by the same principles, the same equations that govern the top one. So let's look a little bit at what that is, and we'll see how we can actually go about and solve that. And later today, we'll solve this ourselves analytically and hopefully get exactly the same thing. So if we look at, not that. If we look at this would be, we're kind of skipping back a chapter from chapter 5. We're going back to chapter 4. Why is that so late? So this is chapter 4. (2D) conduction and we call the finite difference model. So you have a little experience now from this last homework set. Problem 1 on this last homework set, you had to use a finite difference method to be able to numerically calculate how temperature was changing with time. We're going to get a chance to do a little bit more sophisticated finite difference model in 2 dimensions. We're not going to focus too much. It's not going to spend too much time on it. But I think we'll do it in a way that hopefully is useful for you to see where these come from and where you could get solutions like this. Obviously, some of these, like the more complicated solutions, we would get with, say, like a set kind of canned computer software. We're going to solve it by hand in Excel, because I think actually doing that process, you learn a lot about what's going on behind the scenes and how these things work, and the different parameters for it. So we're going to do it by hand in Excel, kind of building up some of the equations for it. So the only one on the bottom, the bottom one that's actually 2D, is governed by can't spell. So this is governed by, it would be the heat diffusion equation, but not in one dimension now, it would be in two dimensions. So d squared t dx squared plus d squared t dy squared plus q dot over k equals 1 over alpha d temperature d time. So this would be our 2D heat diffusion equation, right? One that we've seen quite a bit before. We're not going to go all the way up to 3D because the extension from 2 dimensions to 3 dimensions, you don't gain a lot of understanding into what's happening. So we'll just stick with 2 dimensions because we kind of hit all the basics without getting too crazy in our math. And because it's harder to solve things in 3D in Excel because, right, Excel is kind of fundamentally 2D. So we'll just solve it as 2D. This allows us to look at, this equation allows us to look at more complex problems, obviously going from something that's just changing in a single dimension to something like that thing on the bottom where we have multiple dimensions going on. This equation though, because now we have, right, you guys have an appreciation of how messy analytical solutions can get in one dimension, right? We often ran into like weird functions like ERF and cinch and cosh and all these weird functions, Bessel functions for some of it. We had infinite sums and it got a little messy when we were doing things just in one dimension. So a lot of times when we shift from 1D up to 2 dimensions, a lot of times we even lose the ability to have analytical solutions. So there are some simple cases where you can still get nice in quotes, analytical solutions, but a lot of times we lose the ability to have analytical solutions. So we have to, if we want to look at these problems, we have to go to numerical methods. Often, or really typically, not possible. So these need numerical approaches. So, right, the difference is with an analytical solution, we know temperature of X, Y, Z, time. We know that exactly. Okay, so that's the power of an analytical solution, is we know everything everywhere and we know it exactly. With the numerical solution, our goal is find T, X, Y, Z, time at specific discrete points. So the big difference between an analytical approach and the numerical approach is we have to define, like, I want to know temperature right there. What's temperature right there? You're not going to get nice equations that describe it anywhere, like throughout the entire object. You're going to have to say, I want it there, and I want it there, and I want it there, and I want it there. And you have to go and define what points you actually want to calculate it at. And then we're going to build up equations that allow us to calculate it at those individual points. So this is like, if you look at the picture that you have, it'd be basically like, okay, all of the nodes in the grid on the sheet that you have, if you look at that, we would be calculating the temperature at each grid point, basically, at each node in the grid. So we're not really learning the temperature everywhere, but we're learning it at specific points in our object. And then we can try to figure out how we can use that information to calculate things like heat transfer and different things like that we might want to know. So we'll look at a simple example, again, kind of trying to build up the bottom picture on your handout. So we'll look at consider a 6 centimeter by 8 centimeter object divided into like a 1-by-1 grid. So we're going to look at a numerical solution of something like this. We have a 6 centimeter by 8 centimeter object. In this case, right, we can put some axes on it, so that we'll call that the Y, not the C. Call that the X. And what we want to do is divide it up into a specific grid work. We're going to solve, like I said, we're going to solve this bottom 2D thing on the assignment that I gave out. So if you look at that, okay, we maybe got the size wrong, but if you look at that, what's happening on that object, the top is at 20 Celsius, and then the sides are at 100 Celsius. So that's how we're going to define our thing. So the top surface, I don't know why this program does this every once in a while. Sometimes like a 2-point line is really huge, and then other times you open it up and 2-point is really thin, and I don't know why. Okay, so this is, we'll call this TB. So the top surface here is TB. And then we have a surface here on this side that's TA. Surface on this side that's TA. And a surface over there that's also TA. So we have 3 constant temp sides that are at, say, like 100 Celsius, and then one side that's at 20. We're going to divide up this guy into a grid. So I'm going to get a line. So we want to do like a 1 centimeter by 1 centimeter grid. Put that there. So there's a grid line. Or let's do a 2 centimeter by 2 centimeter grid so we don't have quite as many points. So we'll do like that. Using my ruler and I'm not actually drawing along it. Okay. So we have this grid. Let me erase this, and this is going to be a 2 by 2 grid. So what we're going to do is divide it up and calculate the temperature at each one of these grid points. Okay, at each one of those nodes. If we look at it, right, we have 4 nodes up and down and 5 left and right. So we have 20 total nodes. Gives us kind of 20 unknowns. It's not going to be quite that bad because we actually know a lot of them already. We know a lot of them are TB and a lot of them are TA. We'll look at one of the inside ones because the outside ones are fairly easy, but we'll look at one of the inside ones. We can label them by like where they specifically are. So we could label this as, say, T11. This would be T21, T31, would be T12, T22. I'm not going to label all of them because you kind of get the point. So we'll look at a specific inside node. It will be a general one. We'll look at an inside node TMN. So if we look at what that looks like, so we'll look at it just in one dimension first. So TMN is there. And then there's a node over here. This would be TM, TM plus 1, N. And over here on the other side is TM minus 1, N. So those are the two nodes, like the one to the left, the one to the right. What we're going to do is also consider, and this is to be able to get us a little bit more accurate, a more accurate calculation. What we're going to look at is the spots halfway in between. So this is T, like M plus 1/2 N, and Tm minus 1/2 N. And if we look at that, this has a dimension here from there to there of some dimension in the x direction. If we look at our example, that would be 2 centimeters, right? That's our spacing between grid points. So this would be 2 centimeters. Okay, if we looked at our node TMN, we're going to try to we're trying to do this equation numerically. So we need to figure out, like, what is that? How is temperature? What is d squared T dx squared? But get a numerical approximation for that. So we're going to look at our node d squared T dx squared. Okay, so that's going to be about, right? So if we looked at the like just the slope, the first derivative, that's going to be approximately equal to like the value at Tm minus 1/2, the value at Tm plus 1/2 divided by delta x. That would be like the first derivative. So the second derivative is approximately equal to the slope evaluated at m plus 1/2 n. So the slope at kind of the right-hand side minus the slope at the left-hand side minus dt dx and minus 1/2 n all over delta x. Right. I mean, if maybe we're more used to thinking like, how would we do this as a first derivative? If we think about this method, what we're trying to look at is, make this comment in a different, we look at our previous numerical method, this would be like homework number, what is this, homework 6? This past homework? So if we look at the method, the numerical method we used on that problem, we had a function that, so this is our real function. And what we did is we took a point here, n, and then we extrapolated the slope at that point to the next point. So we took that and extrapolated that to the next point, n plus 1. And then we calculated the slope at n plus 1. And then we took that and extrapolated the slope to n plus 2. So we were always kind of taking the slope at one point and extrapolating it to the next point. Remember that when you set up your, hopefully you had a chance to at least go through this problem a little bit, but when you set up your equations, you take, the slope at time 0, and you use that to extrapolate out what the temperature is going to be at 5 seconds. Then you take the slope at 5 seconds and use that to extrapolate out to 10 seconds, and then to 15, and then to 20. So we're always taking like the first point and extrapolating to the next point. You can see just from my picture that that's not the greatest method, right? If you have something that's changing really quickly, you can actually undershoot it quite a bit. Even the example sheet that I posted, where we use this method to calculate like y equals x squared, something simple like that. We undershot even a simple function like that. And after a little while, you kind of miss the actual answer. So this method introduces quite a bit of error. So what we're going to do on this, this top method, we have, okay, if we have a real function like that, and we want to find n, what we're doing is basically looking at, so n minus 1/2 and n plus 1/2. And we're connecting those with a line and using that to estimate the slope at position n. So this estimates okay, so we use a point to the left, a point to the right. We calculate the slope between those points and use that to estimate the slope at the midpoint. So this is, I mean, just from the picture, you can say that's going to be a better estimate of the slope at point n. There are still functions, right? There's still error involved. It's still just an estimate. It's not an exact solution because this is a numerical method. But it's better than what we were doing in the past, kind of our super simple method. So that's why we're doing it this way. So if we look at, again, this this equation here, this top equation. If we're looking at that and trying to solve it, we now need numerical estimates for dt dx at both of these locations. So the temperature dx evaluated at m plus 1/2 n. This is equal to, okay, so what's the, I'll go back up to my picture. So the slope at this midpoint here is equal to this temperature minus this temperature divided by delta x, right? So this guy equals T m plus 1 n minus T m n all over delta x. And right, d temperature dx at m minus 1/2 n is about equal to, I shouldn't have equal signs, I should have about equal sign, about equal to T mn minus T minus 1n all over delta x. Okay, so d squared T dx squared is about equal to this stuff together. So if we look at this, we have a, right, we're subtracting, again, let's look at what we're doing. We're taking this term here and subtracting this term. So we're taking the difference between those and dividing everything by delta x. So we're taking this term minus this term. So what that will give us is T m plus 1 n minus T m n minus T m n minus T m minus 1 n all over delta x squared. Or we can write that a little bit more compactly. This is going to be T m plus 1 n plus T m minus 1 n minus 2T m n all over delta x squared. Okay, we could do the same thing in the y direction. In y, we would get d squared T dy squared. This would be T m n plus 1 plus T m n minus 1 minus 2T mn all over delta y squared. These should be getting lazy. Approximately equal to. So if we have a situation where our object is steady state and there's no heat generation, right, steady state, so partial t, partial time equals 0. If those two things are true, that simplifies our partial differential equation. Then we would get 0 equals d squared T dx squared plus d squared t dy squared. So we could put these two things together. This is going to be a lot of t's with subscripts, and I realize that we'll look a little bit about how some of this stuff simplifies out. But this would be t m plus 1 n t m minus 1 n minus 2 tmn all over delta x squared plus t n plus 1 m n minus 1 minus 2 tmn all over delta y squared equals 0. Okay, so lots of subscripts. The handy thing, so these two things have, in general, they could have different denominators. But if we look at what we did for our problem, we made delta x and delta y the same. Right? We made it was a 2 by 2 grid. So delta x is 2 centimeters, delta y is 2 centimeters. So all of this is a common denominator. So we just happen to use delta x equals delta y. And if that's the case, then that makes our lives easier by a lot. So this is 2 centimeters in this case. Right? This could be 2 microns. It could be, 3 nanometers. It does, I mean, maybe not. So it could be whatever dimension you happen to choose. It's just whatever grid you decide to put on your object. But if you choose it the same in both directions, then everything is on a common denominator, above a common denominator. So we could multiply both sides of the equation by, say, 2 centimeters squared. And that's going to cancel out the delta x squared, and it will cancel out the delta y squared, and it will get killed off by the 0. So then we would by 2 centimeters squared in this case, and that would give us t m plus 1, m plus 1 n t m minus 1 n plus t m n plus 1 plus t m n minus 1 minus 4, well, I'll write it this way, equals 4 tmn. Or, if we're solving for this, which is what we're trying to do, we're solving for the temperature at this discrete point, we get this super easy equation. So t m plus 1 n plus t m minus 1 n plus t m n plus 1 plus t n minus 1 all over 4. I'll box that. This is, let's look again at what we're looking at. So we're looking at right, this grid point. So this is our grid point MN. We have one above, we have one below, one to the left, and one to the right. So this is minus 1 n would be m, n plus 1, m plus 1, n. Okay. So at steady state, we can think of, so the temp at this grid point is the weighted average, sorry, not the weighted average, just the average, is the average of its 4 surrounding temperatures. So how do you find the temperature in the middle? Well, you take the temperature above it, the temperature to the right, the temperature to the bottom, the temperature to the left, you add those all together and divide by 4. So let's look at how this plays out in practice and actually solve for, and we could write this same equation. So this would be true for any of our interior locations. So let's set this up and see how we would actually solve it. So we have a grid, right? I'll redraw it because it doesn't take too long. So we have this is 8 centimeters, this is 6 centimeters. Something like that. Should have 4. Okay, we have something like this. And again, if we label our, or if we don't, if we label all of these nodes, this would be T11, this is T21, T31, T41, T51, T12, 22, T32, T42, 13, 23, 33, 43, 53, T okay, the 24, 34, and 54. So those would be all of our temperature nodes. We can first apply the boundary conditions. So we have boundary conditions. We have 4 boundary conditions. Sorry. We have boundary conditions at the top, the left, the right, and the bottom. So our boundary condition at the top was 20C, or what we called T. So this would be TM4 equals, we called that TB. Then we have T of the left-hand side, so that's T1N equals TA. T of M1 equals TA along the bottom and along the right side. So that's T of 5n equals TA. Okay, so we'll say the left-hand side, the bottom, the right-hand side, those are our boundary conditions. Then we're still left with 6 unknown temps, the 6 in the middle. So we have to set up equations, 6 equations. We have 6 unknowns. So our equations, we have T23, T33, T43. So that's the top, and T22, 32, and 42. So T22, 32, T42. So those are our 4 unknowns. We have to write 6 equations because we have 6 unknowns. So this gives 0 equals, right, this one's going to be the weighted average of the 4 around it. So we're looking at first that temperature. So it's going to be the top, the right, the bottom, the left. So that's TB at the top, T33, T22, and then TA at the left. So that's TB plus T22 plus T33 plus TA minus 4 T23. So that would be our equation for that guy. We could write a similar equation. So for 33, TB plus T23, 32 plus T43 minus 4 T33. Okay, so those are, again, the 4 around it. So that's looking at this next one. We have 3, 4 at the top, 4, 3 at the right, 3, 2 at the bottom, and 2, 3 at the left. Then we move on and write, okay, an equation for this one. So it's going to be TB at the top, A at the right, 4, 2 at the bottom, 3, 3 at the left. This 0 equals TB plus TA plus T42 plus T33 minus 4 T43. Okay, so we can write this. I'll actually skip these because it's basically the same thing. If we look, though, we could formulate this. We're going to have 6 equations. We have 6 unknowns. To solve it, we can solve this system of equations using matrix algebra. So the matrix that we would have a coefficient matrix. We would have a vector of our temperatures. And that equals C. So this would be our coefficients. That's our unknowns. And this is our knowns. So let's look, rather than writing out all of the equations, we're just going to look at, okay, how would we put this in? So if we look at the matrix that we would set up, it's going to be kind of big and ugly. We have our 6 unknown temps. So here, 2, 3, T, 3, 3, T4, 3, T2, 2, T3, 2, T4, 2. So those are our 6 unknown temps. So right, it's going to be right. Our matrix math is going to work where basically these. I'll just write this to kind of help us as we put our coefficients in. So this is going to be the coefficient on T23. This is T33. This is T43. This is T24. No, sorry, that's T22, 22, T32, and T42. Okay, each of those columns. So if we look at our first equation, we're translating this first equation here down to the bottom. So we're going to put all of the knowns on one side and the unknowns on the other side. So this is going to be, so our knowns will be TA plus TB. So on this side, we have TA plus TB. And on the other side of the equation, we would have a positive 4 T23. So we're going to put a 4 in that coefficient spot. We have so positive 4 T23, and then we would have a negative 1 T22 and a negative 1 T33. Okay, so we would have a 4 there, negative 1 T33, and a negative 1 T22, and we would have zeros in the other spots. Okay, so we would translate our first equation into this matrix problem. We would do the same thing with all of the other elements. I'll just fill out the matrix because after you do it once, we're never going to do it again, really. This would be negative 1, 0, negative 1, 0, TB. So that would be our second equation. So again, we have a positive 4 on T43, and we have a negative 1 on this one, off of an equation. Positive 4 there, we have a negative 1 on this one, and this one, and that all equals TB. So we should have, a negative 1 on the right things. Again, I'll just fill out the rest of this. Negative 1, 4, 0, 0, negative 1, TA plus EB. This would be negative 1, 0, 0, 4, negative 1, 0, 2 TA. For our T22 equation, 0, negative 1, 0, negative 1, 4, 0, and TA. For our T32 equation, 0, 0, negative 1, 0, negative 1, 4, 2 TA. Okay, so this would be the easiest way to solve, well, maybe not the easiest way. How many of you like shudder a little bit inside when you see me set up a matrix problem like this? Any hands? A little bit? So this was with only 6 unknowns. What if we wanted to do a more accurate calculation that say had like 1,000 grid points? How big would our matrices get? It would be in a 1,000 by 1,000 matrix, and it would be super gross. So when you build up larger of these, this is how we actually do these problems. So we would now solve the matrix. We could solve, like this one, we could solve by hand. You guys could solve by hand. Okay, you might have to like get out your math textbook and remember how do we solve matrices again. But I promise you, you guys could solve this one by hand. But obviously, if we went to something like 100 by 100 matrix or 1,000 by 1,000 matrix or a 10,000 by 10,000 matrix, that very quickly gets to be something that you can't solve by hand. We are not going to focus at all in this class on solving these matrices. Maybe that gives you a little bit of joy inside. Hopefully it does. We're not going to do that. There is a part in your book where they go into like, how do you actually solve these computationally? Like what are the analytical methods? If you're interested in that, I would at least flip to this. I think it's at least interesting to like scroll through it for 2 minutes and go, huh, okay, and then close it. So our book shows the Gauss-Seidel method. So it's actually, it's really a pretty difficult thing to solve large systems of equations quickly. So if you want to do something like this, if you're wanting to build the background of a program that's doing, say, like a 2D modeling, whether it's for heat transfer or for, stress in a beam or for whatever it is, you're using the same kinds of methods. Whatever it is you're trying to do to actually solve these large systems of equations that you end up getting in all of these types of problems, you use the same ideas, like you set it up like a matrix and then use some fancy math method that I don't understand to actually be able to plow through that and solve it as quickly as possible. That's any of modeling software, engineering modeling software. This is how they're modeling it. They're setting up large systems of equations like this and then plowing through that with basically fancy matrix math techniques. So the Gauss-Seidel method, I think, again, this is in, I have written down Appendix D. So like I said, don't spend real time on it, but I do think it's worthwhile to at least like spend a couple minutes, pull up Appendix D, scroll through it, be a little amazed. Like this is how this stuff is actually working. What we're going to do in this class is not the math problem. We're going to do, again, just to try to, I don't really particularly care that you know how to solve that because there are other people that know how to solve that. But what I want you to do is get a little bit of a feel for how we set up these problems and how they work and interact. So what we're going to do, we'll focus in this class on just setting up the problems, really. So how do you handle boundary conditions? How do you set up the equation? We'll do some basic models. So we'll on setting up problems. And we'll use a guess and check solution method. And maybe for those of you who have used Excel Solver, you know a little bit. We're not going to use Solver because Solver actually doesn't do this exactly as we want it to, but we'll use Excel to run kind of the same thing. So we're going to set up a system of equations that does this. So we'll give it, so our method will be using Excel. We will provide an initial guess. So we will like plug that in and use that to calculate our unknowns. Then we'll take that and we'll compare our new calculation to the previous value if we had a previous value. So we'll compare it to like what our initial guess was. So we'll put an initial guess in, use that to calculate things, then compare it to with what our initial guess was. So then we'll look at, is our new temp close to what the old one was? Yes or no? So if no, we go back in our loop. So if no, we're going to keep going around and say, okay, but now use this new value and recalculate things. Are we close now? Yes or no? Okay, still no. Recalculate things. Are we close now? No, we're still not close. Recalculate things. So we'll keep going around in this loop. But once we finally are, say our temperature, our initial guess was, or our old value was 293.4 and our new value is 293.39. We go, aha, we're really close. We're converging on a solution. That's when we're going to pop out. And we'll call that our solution. So we're going to look at how we do this in Excel, and we'll spend the last, I guess, 13 minutes. I'll pull up Excel and we'll solve this problem and hopefully even make it look colored like this, which is kind of fun. Things you didn't know Excel could do. Okay, so as I'm pulling this up, we're going to be doing more of this on Tuesday. So Tuesday is going to be kind of a weird class. I have some notes about it on Moodle, but Tuesday we're going to be bringing our laptops in and kind of doing like a work day. So there are a couple things. There's going to be a video that I post on Moodle shortly after class today that is worthwhile watching, looking at how we can handle boundary conditions. Right, this problem has the easiest boundary conditions that we could have because they're just constant temperatures. But say we have convection at the boundary, how do we handle boundary conditions? We'll look at that. We'll only do convection because kind of once you do that, you get the hang of it. But kind of to prep for Tuesday's class, and I will give the plug, like if you prep for Tuesday's class, you won't have homework for the next while, which will be kind of a nice thing. So this is like our next homework is going to be prep for Tuesday. So you're going to work on that. There's like an in-class, it's not in class because you'll be doing it beforehand, worksheet to go through looking at boundary conditions. And then if you're not done with that, or if you didn't start with that, then okay, when you come to class, then you'll work on that while other people are working on the homework set. But that's going to be, so hopefully we'll come to class Tuesday, bring your laptops, bring Excel. Hopefully you've had a chance to do some of the prep work beforehand. Kind of the more you do, the more like nitty gritty, this isn't converging and my solution stinks. We can work through those problems and you're not, because some of the stuff that we're going to do is using Excel in ways that the business people that made Excel didn't want it to be used in, but we'll do it anyway because it's fun. But that means it doesn't work super great at what we're doing, but it works okay, and it's nice because it's very like manual. So I think you kind of get a feel for like what's actually happening. But because it's Excel and not like built for this, if things go wrong, your solutions can blow up and you can like never get it back again. So I'll help you work back through that if that does happen. But we'll be working basically on the next homework set, as well as this in class, and kind of wrapping this stuff up with kind of a weird work day next Tuesday. So take a look at some of that info, hopefully before. So we'll make this our grid. Okay, so I'll make it squares so that we can see a little bit. Okay. So we'll look at, okay, so our top was 20 Celsius. I don't know how many squares we'll need. How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We'll make it 10. So we'll do a 10 by 10 grid. So the top is 20, the sides are 100. So that's 1, 2, 3, down to 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So that's 100. Now over to here. Now over to there. So the hardest part about these problems is setting up boundary conditions. Now we have to give it an initial guess. So I don't know, let's call our initial guess 30, because it's somewhere in the middle, and we'll just say like it's 30 everywhere. Okay, so we have to give it some initial guess. Then what we're going to do is go through, and we want to program each of these cells in the middle is going to be the average of the 4 cells around it, right? This is going to be the average of the 4 temperatures around it. So we can say this is equal to this one plus this one plus this one plus this one. Okay, and I'll have to do all divided by 4. Divided by 4. So Excel is more than happy to do that. But now I have to do the same thing for its neighboring cell. So this is equal to this plus this plus this plus this divided by 4. Okay. So Excel just did that. I think I left this on. So yeah, I shouldn't have done that. Okay, so if we do that again, so I can just copy this formula over. And it looks like things are happy. If I tell Excel to calculate now, it goes crazy. Because it says, like, I can't calculate that one because that one depends on this one, and I can't calculate this one because this one depends on that one, and it freaks out. So normally you can't have circular calculations in Excel because Excel doesn't like that. I don't know if you've ever messed with that or ever accidentally done that, where you have like one term calculated from another term, but that term's calculated from the first term, and Excel gets scared because it's like all in a circle. So it says there are one or more circular references where a formula refers to its own cell, either directly or indirectly. This might cause them to calculate incorrectly. Try removing or changing these references or moving the formulas to different cells. So you see, okay, so it says, those ones depend on each other, and I don't like that. But that's exactly what we want it to do, because Excel doesn't always know what's right. So we're going to change it. And this is where, again, some of the options are weird. So we're going to change a couple options. If we go to, it's the same basic structure on a Mac if you have a Mac, but you go to the options, formulas. Typically, like a workbook will have automatic calculation. So like when you plug in a formula and hit enter, it'll pop out your answer. It's going to be better for this if you like give yourself the time to set everything up, make sure it's ready, and then calculate like on your own terms. So typically I had this set up already. Typically we'll set the workbook calculation to manual. And then if you look at the little like blurb that pops up, you probably can't read that, but if you hit F9, it tells you if you hit F9, that means, okay, go, calculate. So we'll turn on manual calculation, and then when I hit F9, it will calculate. I'm going to change the maximum iterations to 10 so we can kind of see things working. But we're going to enable iterative calculation. Right? This is exactly what we're trying to do. We're trying to iterate and say, okay, this is our initial guess, recalculate things. Did that change? Okay, go back around in the circle. So this allows us to go through this little calculation loop 10 times before it stops. So it either stops after 10 times around the circle, or it stops if the maximum change is 0.0001. So if it calculates, okay, it's 45.539, and the next time it's 45.5395, it says, okay, that's close enough, we'll stop. So you can change kind of what sensitivity you want. You know, how close to the last value, how close is close enough. So we'll turn on both of those things, manual calculation, so I'm telling it when to do it again, and iterative calculation. If we do that, then, so each of these cells in the middle, where things actually get fairly straightforward, they're all the same, right? Like this one is equal to the 4 around it. So I can just click and drag for these interior nodes. I can just click and drag, and Excel will handle the math for like the cell references for me pretty well. So this is the 4 around it. This is the 4 around it. So once you get, so I have now the boundary conditions all set up, constant temperature. I have all of these interior nodes set up. The last thing that I'm going to do, just to kind of make it pretty, I'm going to select all of this and go to conditional formatting, which is up here. And we'll use a color scale where, okay, red is hot and green is cold. So it's so it automatically picks the colors. The big numbers are going to be red. The small numbers are going to be green. Okay, and then I'll, okay, so now I have everything set up. I'm ready to go, so we'll push F9. See what happens. Isn't that kind of fun? We'll push F9 again and see, okay, so now you can see the numbers are still changing a little bit. If you like look at just this one, 37.937, if I push it again, 38. 38.1. So you can see they're changing just a tiny bit, tiny bit. Okay, now they're changing less. Now there are a couple decimal, every time I push F9, I'll push it again, you'll see maybe 1 or 2 decimal places somewhere change. Okay, and now it's pretty much done. Now they're all basically stuck. But you can see, right, okay, so we used a pretty big and coarse grid. If we had used more cells, and it wouldn't have been that hard to set up actually, we could have really exactly reproduced this bottom picture. I mean, we did exactly reproduce it. We just have a fairly coarse grid. The challenge will be the inside is easy. It's just the average of the 4 cells around it. The outside, the exterior of the shape is going to be a little bit trickier. Turns out it's not actually going to be that much trickier, but it'll be a little bit trickier. But we're going to be able to use this to, again, try to get like a little bit of a manual handle on how software does stuff that numerically that you can't do analytically. So we'll play around a little bit with that. Like I said, I encourage you to take some time before Tuesday and work on some of the stuff that I'll have laid out. If you can't do that and just show up Tuesday, like still come to class Tuesday, because you can then get ready on some of the stuff that you could have done before class, and I think it will still be fine and valuable. But I think the more you can get kind of through some of this before stuff, I think it'll make your homework life easier afterwards. So my little plug for working ahead a little bit. But with that, it's 9:20, so we'll say happy weekends to everybody.